Now, what is going to help us to make comment on the strength of the dependence here? It is going to be called correlation. So the second measure, correlation here, is going to help give us information on how two random variables are related, but it is a better measure. Why? Because the covariance does not indicate anything about the strength of the relationship. Okay, so covariance is indicating just the type of the relationship, but covariance is a correlation is indicating both the strengths and the type of the relationship. So how do we compute correlation? Now, in order to calculate the correlation, you first need to calculate the covariance. Okay, first the covariance. So even if I say correlation is a better measure, I mean, it requires calculation of the covariance. Okay, so without calculating the covariance, you cannot calculate the correlation. And after calculating the covariance, you need to divide the covariance to the square root of the product of individual variances or marginal variances of these random variables. So covariance of x and y divided by the square root of variance of x times variance of y will give you the correlation between x and y. And let's see the further properties of the correlation. Correlation of x and y is equal to correlation of y and x, just like the covariance. The correlation is a symmetric relationship, and correlation values between two random variables can be -1 at minimum and +1 at maximum. So unlikely to the covariance, covariance can be any real value. It can be positive or negative, and it can be zero as well, and covariance can take any value. However, correlation can only take values between -1 and +1. So any real value between -1 and +1. And if x and y are independent, you know the covariance is going to be zero. And if the covariance is zero, the correlation is also going to be equal to zero. So when x and y are independent, the correlation will be zero. Or in other words, if the correlation between two random variables is zero, x and y are going to be independent. Now, again, let's answer this interesting question. What is the correlation of a random variable with itself? Now, if you use the correlation formulation, correlation of x with itself is the covariance of x with itself divided by the square root of the variance of x times variance of x, which is going to be equal to 1, because the covariance of x with itself is equal to variance of x, and that is going to be equal to 1. So a random variable, it is correlated with itself with correlation measure 1. What is the correlation of a random variable x with its negative? So what is the correlation between x and -x? And that is going to be the covariance of x and -x divided by the square root of the variance of x and variance of -x. Now, that negative coefficient, -1 coefficient in front of x in the covariance can get out of the covariance. However, that negative -1 inside the variance gets out of the variance by squaring it, if you remember. Any coefficient in front of the random variable inside the variance gets out of the variance as being squared. And that square will make it is equal to 1. And that covariance is equal to variance of x, and minus variance x divided by variance x will be -1. So the correlation of a random variable with its negative is going to be -1. Generally speaking, you can also practice this correlation operation with the above formulations, just like the above formulations. But generally speaking, if you are interested in the correlation of a random variable with its any linear transformation, ax plus b, the correlation of a random variable with its linear transformation is going to be equal to 0 if the multiplier a is equal to 0. If the multiplier a is positive, then the correlation will be equal to 1. And if the multiplier a is negative, then the correlation is going to be equal to -1. Now, of course, we are always talking about specific examples here. Now, let me tell you that we may have correlation values between two random variables which are different than -1, 1, or 0. So the correlation can be any value, any real value between -1 and 1. If the correlation between x and y is close to -1, this means there is a negative linear dependence relationship between x and y. So you see this is a linear relationship, but we can see that linear relationship when the correlation is -1 or 1. But here it says it is not -1, but it is close to -1. If the correlation is very close to -1, we say that there is a negative linear dependence relationship between x and y, but there is also a random component of each other as well. So they are dependent on each other, but not exactly with a linear function. So this means when x takes high values, y tends to take low values, or when x takes low values, y tends to take high values when the correlation is close to -1. And that dependence is very strong, not as strong as this linear function, but it is very strong. Okay, maybe some of the variance in one variable can be explained as a linear function of the other variable. For example, if this correlation is very close to -1, we can use the observation on one random variable to predict the other one. For example, if x is the price of a second-hand automobile and y is the odometer value, the correlation between these two values is going to be very close to -1. This negative linear dependence is going to be very strong. So still, even if you know the odometer value, you cannot exactly predict the price of a second-hand automobile, but your prediction is going to be much more accurate because the dependence is very strong. I mean, the experts who are defining the price of the second-hand automobiles are basically looking at the odometer values and other variables as well. I mean, this linear dependence is not an exact linear dependence because the price of a second-hand automobile is not just dependent on the odometer value. It is also dependent on other factors as well. But even the relationship between the price of a second-hand automobile and the odometer value is very strong. And even the observation of the odometer value is almost enough to get an accurate prediction about the price of a second-hand automobile. So this negative linear dependence is very strong if the correlation is close to -1. Now, if the correlation is close to 1, this means there is a positive linear dependence relationship between x and y, and that relationship is very strong. Okay? So whenever the random variable x takes high values, y tends to take high values too. Or whenever x takes low values, y tends to take low values too. For example, if x is the grade of students in physics 108 for midterm exam and y is the grade in the same student in the final exam, if, for example, if in the midterm the student is above the average, then we expect the same student to be above the average in the final exam as well. So this is just an expectation. And my friends, unfortunately, I mean, even if I am doing multiple exams for you and homeworks for you, I mean, this is usually the case. Mostly, if a student takes a good grade in the first midterm exam, in most of the cases, that student does the same thing in the second midterm exam and in the final exam. Only there are a few exceptions. Okay, so we would like the students who get a low exam grade in the first midterm exam to be that exception. So exceptionally, they are going to take above the average in the final exam. So we would like to see that, and we see that for a few students only, but generally speaking, we do not see it. Okay, so whatever student takes in the midterm exam, first midterm exam, if it is lower than the average, then the final exam is going to have the same situation. So the correlation between the midterm exam grade and the final exam grade is very close to 1, and that positive linear dependence is usually very strong. Okay, and if correlation between x and y is equal to 0, this means there is not a relationship between x and y. Actually, this is a wrong sentence. The fact that the correlation is equal to 0 does not say that there is no relationship. It says there is not a linear relationship. Okay, So I need to write here, I need to change that. I am sorry for that. There is no linear relationship between X and Y if the correlation is 0. So X and Y are linearly independent, we say. Linearly independent. But this is what we know as independence. Actually, we have defined the independence as a linear independence. So in this class, when we say independent, this means they are linearly independent. Okay? So there are also non-linear dependent structure as well, but I do not want to confuse you with that. So you see, if the correlation is equal to 0, this means these two random variables are independent. There is not a linear relationship between X and Y. For example, if X is the number of ships passing through the Bosphorus Strait on any day, and Y is the number of mobile phones sold in Jawahir shopping center on the same day, I mean, you do not expect any dependence between these two values, right? I mean, nobody purchases more and more mobile phones just because many ships has passed through the Bosphorus Strait, right? So usually we see that the correlation between these two values is 0, okay? Now, please do not confuse the correlation with causation, my friends. Causation and correlation, they are two different things. So let me write these two words to you, okay? And in fact, these two things are two different things, correlation and causation, okay? So what are these things? Now, causation means the fact that an event occurs triggers another event. For example, when an earthquake occurs, most people live outside their house for a few days, right? So this is a cause and effect, causation. Okay, there is a causation here. But correlation does not indicate causation. For example, when we observe the demand in ice cream, okay, when the demand for the ice cream increases, also the shark attacks in the sea, in the ocean increases. Okay, now are the sharks attacking people just because people eating ice cream more, or the people are eating the ice cream more because the sharks are attacking people in the ocean? Actually, there is not a cause and effect situation here, but these two events are correlated. Why they are correlated? Because we know that the sharks are attacking people in the summertime because the people are swimming in the sea, and also people are eating ice cream in the summertime. Okay, so these are correlated not because one event is triggering the other one. One is the cause and the other one is the effect. Okay, so when you see correlation, between two random variables, do not think that they are having a cause and effect relationship. Okay? So causation can be extracted by social sciences. Correlation can be extracted by statistical sciences. Okay? So correlation is the thing that we are interested in. Now, if I give you the same example here, the price of the second-hand automobile and the odometer value, I mean, there is also a causation relationship here as well. I mean, they are negatively correlated, but you can also explain the cause and effect, because the more you use the automobile, then it is going to depreciate faster, right? So if you run an automobile for maybe thousands of kilometers, then the automobile is going to depreciate fast, and when it depreciates, its value, the second-hand price, is going to decrease as well. So we can explain the cause and effect relationship here, but not every correlation can be explained with a cause and effect situation. Okay, so remember now, there is a correlation between the number of shark attacks and the demand to ice cream. However, the sharks are not attacking people because they are eating ice cream, or the people are not eating ice cream because the sharks are attacking them. Okay, so please try to understand that correlation cannot be explaining the causation. Okay, so we cannot derive causation from correlation.